Well, hello to all my physics pals. Paul Lake here with another physics problem solved. This is the channel where I solve the physics homework problems provided to me by my tutoring clients. Take a look at the video description for a way to get in contact with me if you would benefit from a private physics tutor. My rates are reasonable and I'm pretty good at this. And if you find this video helpful, please like, share, and subscribe if you're a physics student or a physics teacher. If you're a physics teacher, please use my materials. I would be honored if you did so. Then let's get to today's problem. It is a kinematics problem where we're going to figure out the average and instantaneous velocities and accelerations given a position versus time function. And in order to solve this problem, you will need to understand how to find average velocities and average accelerations. You'll also need to know how to find instantaneous velocities and accelerations. And we do that, of course, using the derivative. And we're specifically going to use the power rule today. So hopefully you're somewhat familiar with these ideas, and we're going to use these ideas to solve today's problems. So anyway, let's read the problem. It says an object moves along the x-axis according to this equation. X as a function of time equals 3t squared plus 2t plus 3 meters. Now, I don't really like it when they express equations like this, but this is what I was given, so we're going to use it. I prefer these coefficients like this 3.00. It'll actually have units of meters per second squared, and this 2.00 will have meters per second, and this should just be 3 meters. But this is what was given, and so we're just going to go with it. Now, determine A, the average speed between 2 seconds and 3 seconds. B, the instantaneous speed at 2 seconds and 3 seconds. C, the average acceleration between 2 seconds and 3 seconds. And the instantaneous acceleration at 2 seconds and 3 seconds. Okay, so what I hope you'll do is try to solve this problem yourself. Pause the video right now and go through it and see if you can solve it on your own. If you get stuck, or if you just want to check your work with mine, hit play and watch the rest of the video or skip around through it as needed. So, okay, well, let's get going here. What's given? What are we given? Well, we're just given this position function. My position on the x-axis as a function of time is equal to 3.00 times time squared. Now again, this is what's given in the problem, but this really should have units of meters per second squared in here. Because then if you have squares, if you square seconds here, plug in dimensionally, the square seconds cancels the second squared, leaving just meters, which is what position is measured in. But they didn't, so let's just not worry about it. Same is true with this. This should be 2.00 meters per second times time will give us meters, and then just plus 3.00. And the units for all of this at the end, it will be meters. And then what are we trying to find? Well, for part A, we want the average speed between 2 seconds and 3 seconds. Now, average speed in this context is just going to be the average, the magnitude of the average velocity. That's what I'm going to say. And so what we want is we want the average velocity. We're going to take the absolute value of it. And now average velocity, well, oh, I don't want to solve it yet. Hold on a second. And then this is between t equals 2 seconds and to 3 seconds. And you know what? I'm gonna write this out a little bit differently. Hold on a second. Sorry about that, because I want this to be really clear. We want between these two times. We want the average velocity between t equals 2 seconds and t equals 3 seconds. So this is an interval of time. And you'll see why I'm making that distinction here in a minute. Now for part B, we want the instantaneous velocity or speed at t equals 2.00 seconds and t equals 3.00 seconds. So we want the instantaneous velocity at 2 seconds and the instantaneous velocity at 3 seconds. So there's no time interval in part B. We have a two-time instance, an instant in time, another instant in time. So we're going to have two answers, two different instantaneous velocities. The average velocity between 2 and 3 seconds is only going to be one answer. Okay, well, let's do part C. We want the average acceleration between t equals 2 seconds and 3 seconds. And then for part D, we want the instantaneous acceleration at t equals 2.00 seconds and at t equals 3.00 seconds. So again, two different instantaneous accelerations, one at 2 seconds and the other at 3 seconds. Whereas this average velocity is the average, this average acceleration is between that span of time, 2 to 3 seconds. All right, so let's solve it. And if you're doing this problem, you're probably pretty early in your physics education, whether in high school or college, or calculus-based physics class. I really want to recommend that you lay problems out like this with given, find, and solve. You write down what's given, you write down what you're trying to find. You don't, in your notebooks or whatever, you don't really have to copy down the problem like this. But if you write it like this, it's very efficient, and it also helps clarify in your own mind what's going on. All right, let's solve part A. Okay. Now, what is the definition of average velocity? Well, average velocity, by definition, is what my displacement was divided by my time. Okay, and so now this is the definition of average velocity. And so let's apply that definition. Anytime you see a delta, that's x final minus x initial over t final minus t initial. Okay, and so we need to plug, well, we know what the times are, right? Between the final time is 3 seconds, and the initial time was 2 seconds. So obviously this is a span of time, or a delta t of 1 second. Now what is x final? Well, x final is the position at t equals 3 seconds. So x final equals x at 3 seconds. So I'm going to plug in 3 seconds into the position equation. So that's going to be 3.00 times 3 seconds squared. And again, I'm not going to include units here because they didn't in the problem. Later on, in almost all my videos on kinematics, in all physics videos, I include units. And I'm a real stickler with that. But I guess I'm not today. All right, plus 3. All right, and this will all be in meters. Okay, so what is this? Well, 3 squared is 9 times 3 is, this is 27 meters, plus 2 times 3, that's 6 meters, plus the 3 meters that we started with, okay? And when you add all that up, you get 36 meters. And that is my final position. That is my position at 3 seconds. So that's x final right here. So I'm going to put that in here, 36.0 or what, well, it doesn't really matter. We're just preserving 3 significant figures. Now, x initial is the position at 2 seconds, right? Because we started at 2 and we went over to 3. So this is my initial time. So that's going to be 3.00. And now we just plug in 2 squared plus 2.00 times 2 seconds plus 3 meters that we started. So this is 3 times 4, that's going to be 12, plus 2 times 2 is 4, plus 3, so that's 16 plus 3 is 19. So my position at 2 seconds was 19 meters. Okay, so now we're going to subtract, this is my initial position, we're going to subtract this initial position from this final position to get my change in position. Meters. Okay, I'll go ahead and put the meters in there. And now, when you do the arithmetic, 36 minus 19, divided by 1, well, that's going to be 17. And that is my answer. The average velocity between 2 seconds and 3 seconds is 17 meters per second. Okay? Hopefully that's clear. And if something isn't clear, if you have a question, just put it in the comments. I respond to every comment, and put a timestamp on it so I can find it. And but yeah. My channel isn't that big, so anytime I get a comment, I respond to it. Maybe someday my channel will be so big, but not yet. All right, let's now. Here we're trying to find instantaneous velocities, and that has a different definition. What we need to find the instantaneous velocity is we need the velocity as a function of time, and then we'll plug the times in to get those instantaneous velocities. So to do that, I need my velocity as a function of time. But what is the velocity as a function of time is the time derivative of position as a function of time, right? Because this gives me the slope, right? When you take the derivative of a function, you get the slope of that function, and so velocity is the rate of change of position, or the slope, delta. So anyway, so we need to take the derivative of this function. And we're going to use the power rule to do it. Remember, the power rule says if x is a function of time and you have some constant a, which in this case is 3, times t to the n power, well, dx dt will be equal to, well, you keep that a, and then you bring down this exponent, n, and then you multiply that. So all these are getting multiplied together, and you have, but you have to take 1 power away from n, so it's n minus 1. So this is what we're going to be doing to each piece. Now, hopefully you already know this. And so let's take the derivative of this. Well, we keep the 3. And then we bring down the 2. And then we have 2 minus 1, right? N is equal to 2, so 2 minus 1 is 1. And t to the 1 is just t. All right? And now we're going to operate the power rule on this next term. So this is going to be plus. Well, this is like t to the 1 power, so we'll keep this 2. And then we bring the 1 down. This is the exponent. It's t to the 1, really, right? And then we have 1 minus 1, which is t to the 0. Now, t to the 0, anything to the 0 power is equal to 1. so that we're just going to have this 1. Now here, if we operate the derivative on a constant term, it's kind of like, the power rule, yeah, whatever. This is like 3 times t to the 0 power. So when you bring the exponent down, that n is 0, and so the whole thing is 0. That's one way to look at it mathematically, but just think about it. This is if you had a position that didn't have these in it, it was just x equals 3 meters, well, that's not changing with time. So there's no rate of change. As time goes by, it doesn't displace. And so it has no slope, or it has a 0 slope, and a 0 slope is a 0 derivative. So when you operate the derivative on this 3, you get 0. So I'll go ahead and put plus 0. So now, this is simply 6 times t plus 2. So this is my velocity as a function of time. Okay. Now what they want, though, is they want to know, okay, what is that velocity at 2 seconds? Well, all you have to do is plug in 2 seconds. So the velocity at 2 seconds is just 6, and then for t, we plug in 2 seconds, and then plus 2. And so this is equal to my instantaneous velocity at 2 seconds. 6 times 2 is 12, plus 2 is 14. And it will have units of meters per second. Now let's find my velocity at 3 seconds. I just do the same thing. And so my velocity at 3 seconds will be equal, 6 times 3 is 18, plus 2 is 20, 20 meters per second. Hey, look, you see the average is kind of in between them, huh? Not a coincidence. All right. So the main thing I want you to really focus on here is the difference between calculating an average velocity and an instantaneous velocity. They are very different. A lot of, keep that in mind. Just the difference between average and instantaneous. And now we're going to do the same exact thing, but now we're going to do it for acceleration. Now for part C, we want the average acceleration between 2 and 3 seconds. So the average, to find the average acceleration, we want a change in velocity over a change in time, which is the final minus the initial over the final minus the initial time, okay? Now, they gave us, very nice of them to do this, they gave us the same times as we calculated above, so this is going to, the final time is going to be 3 seconds minus 2 seconds, okay? But what is the final velocity? What is the final velocity? Is the velocity at 3 seconds. Oh, hey, we already calculated that in part B. How convenient. 20 meters per second is my final velocity, or my velocity at 3 seconds, minus my velocity at 2 seconds. My initial, oh yeah, okay, 14 meters per second. And so now we go ahead and get meters per second per second. So you have 20 minus 14, and that's going to be 6. And this is going to be 6 meters per second every second. That's my average acceleration. But usually we express the units, we contract this. This is meters. We're dividing by seconds twice, so that's per second squared. So this is going to be 6 meters per second squared. This is just a mathematical shortcut of writing this. This is what it means. Every second, it changes its velocity by 6 meters per second. That's what's going on here, okay? And notice that time, well, I'm sorry, I'm getting ahead of myself once again. All right, now let's do part D. Let's do part D. And we want to know what is the instantaneous acceleration at 2 seconds and 3 seconds. So if we want, so that means we need the acceleration as a function of time. But acceleration is the rate of change, or in other words, the time derivative of my velocity function. So we're going to operate the derivative with respect to time on my velocity equation, which is right here. Well, I'm going to use the power rule again, and let's take a look. What is the derivative of 6 times t? Well, this is like t to the 1, so that's going to be 6, and you bring the 1 down, and then you have t to the 0. Anything to the 0 power is 1. And then if you operate the derivative on 2 is a constant, so the rate of change of a constant is 0. So that's going to be plus 0. And so my acceleration function as a function of time is 6 meters per second squared. Now look at this. Notice that this is not a function of time. Well, there's no time in it. In other words, the acceleration in this problem is a constant all the time for the whole time interval. And so this is a constant acceleration problem, which you're going to study a lot very, very soon. So that's cool. Now, what does that mean if the acceleration is a constant? Well, that means the acceleration at 2 seconds is just equal to the acceleration at 3 seconds. There's no time. The acceleration is just 6 meters per second squared, or 6 meters per second every second. This is my answer for both. Hey, if you found this helpful, please give it a like. That's a nice way of saying thank you. And again, I don't make any money doing this, so I just like teaching physics. And so yeah, and subscribe, and share it with your friends, share it with your instructors. I am a physics tutor, so look in the description if you'd like to get some one-on-one time with me. Do it over Zoom. It's real easy. So anyway, hey, until the next video, thanks for watching, and may the net force be with you always. That is all.